This is topic 3.6, calculating higher order derivatives. So we have a table here, and we're going to talk a little bit about notation and then taking the derivatives using that notation. So let's first take a look here at y, and the first derivative of y is just y prime, second derivative y double prime, third derivative y triple prime. At that point, you're finished using the prime marks, okay? You can't take the 14th derivative and write 14 prime marks. So at this point, we write y and we put the derivative in parentheses. So the fifth derivative would look something like this for the fifth derivative, okay? But we're just going to use the nth derivative. So whatever derivative it is, you replace it with n, okay? Let's look at our next notation. If we're given f of x and we're asked to find the derivative, we have f prime of x, f double prime, f triple prime, and of course, we are back to that same notation in parentheses for the derivative that we're on. So the nth derivative of x looks like that. Now let's go to Leibniz notation, and if we have y, we will use dy dx if we want to use Leibniz notation. Now look at this, the second derivative, and that is not a typo. This is the second derivative of y with respect to x, okay? And look at the third derivative, okay? So now let's go ahead and write the nth derivative, and this is what it looks like. Just the n up there, dy, and then dxn. So those are our derivative notations in one summary. Let's go ahead, and we are going to be finding higher derivatives for many different reasons, but let's go ahead and try example 1. So this is a polynomial. We'll use our power rule. So the first derivative of x, f prime of x, is 6x to the fifth minus 8x cubed plus 10x minus 3. And so now, if you notice what's going to happen, if you keep going, eventually with a polynomial, you will reach 0. Let's do a few. The second derivative is 30x to the fourth minus 24x squared plus 10. The third derivative is 120x cubed minus 48x. The fourth derivative of f with respect to x is 360x squared minus 48. So we just have a couple more derivatives, and eventually that nth derivative will equal 0. Now, sometimes we like to say what n is. Let's just make some notes. The fifth derivative, I'm going to have 720x. The sixth derivative, I'm going to have 720. So from the seventh derivative on, I'm going to have 0. So we could say when n is greater than or equal to 7. You could also say when n is greater than what? You're right, greater than 6. So when n is greater than 6, the sixth derivative still is 720. But when n is greater than 6, so any derivative greater than 6 is going to be 0. I hope that that helps you. Let's take a look at this second example. You know we will rewrite this as x to the 1/2 plus x to the negative 2. Of course, we have convinced ourselves that we should learn some of these by heart, but when you're continuing on with higher derivatives, it's better to continue in that same notation with negative exponents. So let me show you. 1/2 x to the negative 1/2 minus 2x to the negative third power. So what we don't want to do at this point is do this, and that's what I meant. Because we're continuing taking the derivative, and we like this form. We like this x2 powers, whether they're positive or negative form. Okay, let's keep going. 1/4 x to the negative 3/2 plus 6x to the negative 4th. Now this will not differentiate to 0 eventually. Okay, so that's pretty cool. Let's talk about the second derivative with implicit differentiation, and this is important. This is a biggie. There's one very important step. Of course, they're all important steps. Let's take a look. Okay, so we have the sine of y equals x plus y. So the derivative of the sine of something is the cosine of something multiplied by the derivative of the something. You could just say y. That's equal to 1 plus dy dx. Now we're going to gather the dy dx's on the left side of the equation. I'm going to show you a little shortcut with algebra. We know we'll be factoring out that dy dx when we bring this term over here. So why not think about that term? It's positive on the right-hand side of the equation, so it's going to be negative on this side. So cosine of y minus 1 is equal to 1. So convince yourself of that. Subtract dy dx from both sides, factor out a dy dx, and that's what you'll get. Okay, so we have, now we just have a 1 left on that right-hand side of the equation. Okay? Now for dy dx, we'll divide both sides by the cosine of y minus 1. So we're all set up for the quotient rule. And we now have the second derivative of y with respect to x is equal to the cosine of y minus 1 all squared. The derivative of the numerator is 0, and then that's just 0 times cosine y minus 1. And then we subtract 1 times the derivative of that denominator. And the derivative of the cosine is the negative sine of y multiplied by dy dx. Now, we are going to simplify this, and then I'm going to talk to you about what to do. So that's equal to the sine of y multiplied by dy dx all over the cosine of y minus 1 all squared. Now I want you to take a look at this. This dy dx is this dy dx. You cannot take the second derivative of a function and leave it in terms of a derivative. So we have to replace that with what it is. So the sine of y multiplied by 1 divided by the cosine of y minus 1 all over the cosine of y minus 1 squared. Now this cosine of y minus 1 is going to join this in the denominator, this square in the denominator, so we end up with the sine of y over the cosine of y minus 1 all cubed. See if I can redo that parenthesis. It looked like a C. And that is the second derivative. Okay, that concludes this topic.